Well, good morning. Yes, this is actually joint work done between myself and Yatish Patel at Imperial College, and Lee Chang and Andy Wang at Sydney University. Life being what it is, Andy's name was missed off the paper in the programme, and he did all the work. But anyway, all credit should go to all these experimental data here. And it's an example of collaboration. I function in both institutions, and we've got a joint project looking at cuttings. And we use cutting tests. Sorry, we use cutting tests for measuring fracture toughness of materials that are very difficult to measure in routine tests. This is things like polyolefins, which have moduli, low yield stresses, and you get blunting and so forth. This is, if you've not come across it before, it makes it a bit difficult to follow, but this is a particular issue that we've had in this, which I'll try and explain the motivation for this. So we use this orthogonal cutting, where you have a tool like this and you remove a surface layer, and you can vary the angle of the tool here, and you produce a chip. And if you have a thick chip that you're moving, it's like splitting wood, really, where you don't get, you get a, sorry. Yeah. You get a thick chip here, it bends elastically, but when you take the tool away, the chip comes up, it's straight. Now, if you make it a bit thinner, eventually you'll start getting plastic deformation on here, and you'll get a curly chip coming up. Actually, that diagram should come round in a circle here. And that involves energy dissipation. If you make it thinner still, and this comes from the metals field as well, you get plastic deformation and shear along a band here. You get shear failure. I'm clumsy. And in this case, we assume, and in fact in many cases it's true, that you get straight chips because they turn out to be thicker, but they're not curled. However, it's been observed in these tests that although the analysis developed by this works well, assuming that there is no curling in it, in many cases you observe that the chips do curl, and for somebody who's neurotic about these things like me, it's worrying. So we thought we'd go back and do a whole set of materials, some of which were very curly and some of which were not, and measure the curl in the chips and estimate how much energy is dissipated. Right, this is the analysis that we do for this test. You have a tool coming along here, you measure the cutting force that way, and you measure the lateral force. The reason you do that is it enables you to correct the friction without knowing anything about it, like a friction law. And you measure the chip thickness, HC here, and you assume that all the plastic deformation is along this plane, and yes, you assume that all the plastic deformation is along that plane at an angle of phi. You measure these two. HC is generally bigger than H because of the shearing process. And although we assume that the chip doesn't curl, curling is observed. And the question is, does this matter? So we now repeat the analysis, essentially, that we do for cutting. You can calculate the friction force on the surface here from the angle of the tool, know both this and the FC and FP. You can calculate what the displacement is across the surface. So this gives you the friction energy dissipation term. You don't need to know if it's Coulomb friction or anything for that. You can measure the shear deformation out of this because you can work out the shear displacement along the plane. You assume that it's Tresca yielding in that, and so you get a shear dissipation term. And notice that it's proportional to the yield stress here times the yield strain, the shear strain. And in these cutting tests, it's the same in the metals machining. You get really high shear stress. That's a typo, by the way. It should be 2 tan of theta over 2 here. And if you put, for example, that the thickness is the same, you get a factor here of about a shear strain of 2. But things like 1.6, 1.8, that sort of thing, are fairly common in these sort of tests. Now, for the bending test, you can do a fairly simple calculation. That if you measure the radius, the residual radius of curvature of the chip after the test, you can calculate what the energy dissipation is by looking at the plastic moment and multiplying it by 1 upon r times dx. And that the bending term is given by this. And so in the experiments, you have to collect all these curly chips. You measure the thickness, which we normally do, but now you have to measure the radius of curvature. And if you put those all into the theory here, this is the external work, this is the friction work, this is the shear work, and now we've added on a term here for bending. And you'll see they've both got this sigma YH over 2 in, so you get this. You get, you've seen that one. So this is the basic equation for the test. You plot FC plus FT times tan phi, and you can calculate tan phi from the thickness change, and you plot it against this tan phi plus 1 upon tan phi times h. But notice now there's a term in here, which is the bending strain divided by the shear strain. And it turns out that this thing is actually constant. And we've verified that in experiments that I'll show. And it's exactly the same experiment. Yeah. Right, we took 7 polymers with very different yield stresses and moduli. These polyethylenes, polypropylene, and then we took P, which is engineering polymer, and 2 epoxies, one was rubber modified. And so you get yield stresses that vary from the 100 right down to 18 or 20. And then we measured the bending strains, and you see you get values here around about sort of 18%, which is rather a lot, actually. The stress strain curves are very interesting. The polyolefins are like this. There's a non-linearity in the thing, and we're using an elastic plastic model. So you get a yield strain that can vary from something like here to here. Peak is almost non-work hardening, and epoxies actually work softening. And you see this, in fact, reflected in some of the data. And here's the test that Andy did. You use a surface grinder, you take a sharp tool, you fix the tool angle, a sharp tool about a 5 micron radius, and you cut off thicknesses between about 50 and 200 microns. You collect the chips and you measure HC, which is easy to do. But then he sets these chips into cold curing epoxy and polishes them. Now, it's crucial in this thing, when you look at them, that these lovely spirals, and the radius of curvature sort of increases as you go out. And the reason this happens is that when you do it, you turn it up at a particular radius, but it rolls on itself. So when it comes off the machine, it's a tightly rolled strip. Now when you let go of it, the elastic thing springs it apart. And you get a residual radius of curvature in it. But the one that you want is this one at the beginning. So we take this image, believe it or not, digitize it, and then measure the internal radius and the external radius right at the beginning. That's the one that gives you the true amount of dissipation. Here it looks like less dissipation, but that's because of this business that it's constrained as this rolls up. You need a really good patient research student to do this, and I congratulate Andy on the fact that he did this. Right, there's two slides of this, but I just want to show you the sort of data. We vary the thickness from about 50 microns up to 200. HC, you'll see the difference, they're all slightly bigger. These are the radii of and you get the difference between them, just measuring the radii, and the measured HC is very close to these two here. So we're pretty confident in these reactions. Right. So that's the data that you get. It turns out with this data that EB and this is bending strain and the shear strain are approximately independent of H. The ratio we do is the bending strain is about 5 to 10% of the shear strain. You can see it's not going to make much difference. They're also proportional. And these are the results from some of the test data. These are the GC values which we want to talk about. They vary from sort of 2 down to 1 per square metre. And these are the corrected yield stresses. And interestingly, if they're compared with regular ones, the epoxies and peak, you get the same yield stress if you make this correction in cutting as you do in normal experiments. But in the cutting experiments here, the yield stress is roughly double what you get in a measure. So in conclusion, this bending strain is independent of H, and thus changes the slope in those curves by a constant factor. So GC therefore alters the slope of these graphs if you plot the forces against the thickness, but it doesn't change the value of the intercept, which is GC you're trying to measure. The yield stress you measure is now nearer what it should be, which is right. The origins of this are not clear. I did have a graph where we have some theory, but it's probably due to these fairly large bending strains and the Poisson's ratio effect. It's sort of a bit like antiplastic curvature, and it tends to make the thing unstable, which limits the amount of bending strain that you can get in the and I'll leave it at that. Thank you.
Thank you very much.